Hello everyone and welcome to AWS ANZ Summit. My name is Derek Chu and I'm a solution architect based out in Melbourne, Australia. Today, Nathaniel Weldon, a geospatial AI specialist at Geomatic AI, and I will be showing you how Geomatic AI are taking an innovative approach with machine learning to reduce the risk of bushfires in Australia. In today's session, we'll take you behind the scenes of how electricity inspection works, the drivers behind needing to leverage machine learning to improve Geomatic AI's existing vegetation management process, how Geomatic AI and the AWS Machine Learning Solutions Lab work together to build a point cloud semantic segmentation model to identify electricity assets and vegetation in 3D space, how the machine learning solution was integrated into Geomatic AI's vegetation management workflow, and finally, the outcome achieved by Geomatic AI. Before I get started, let's take a step back to review the drivers behind vegetation management. Extreme weather has really become more frequent and intense because of climate change. And further global warming over the next 20 to 30 years is inevitable. Globally, temperatures will continue to rise. In Australia, we have more hot days and fewer cooler days. As a result, bushfires are expected to become more frequent and more intense, and catastrophic fire conditions may render traditional bushfire prediction models and firefighting techniques less effective. In 2009, we experienced one of the most devastating bushfires in the state of Victoria, claiming 2,029 homes and 173 lives. So devastating it is that as many as 400 individual fires were recorded on the 7th of February 2009, widely referred to as Black Saturday. After the 2009 bushfires in Victoria, a royal commission was established to investigate the causes, responses, and how such a devastating fire could be prevented from happening again. One of the key recommendations was an amendment to the regulatory framework for electricity safety. This required distribution businesses to adopt measures to reduce the risk of fires posed by hazard trees. As such, distribution businesses play a key role in safely and responsibly managing network assets to reduce the risk of bushfires. This includes continually inspecting, pruning, and clearing vegetation around power lines to reduce the chance of contact. In Australia, electricity network providers manage over 880,000 kilometers of electricity distribution with 7 million power poles. To understand the scale of the effort needed to inspect and maintain all these power lines in Australia, if we line up all the power lines in a straight line, we'll be able to travel the moon and back and then some. Now, imagine having to visually inspect 880,000 kilometers of power line for vegetation intrusion. One of the organizations helping to address the challenges with vegetation management is Geomatic AI. Geomatic AI have been working with energy distributors in Australia to monitor thousands of power lines, servicing millions of homes, with many of these electricity assets in bushfire-prone areas. Since its inception, they've been developing advanced mobile and spatial technology solutions to solve complex asset and data management challenges in the utility, transport, and government sectors. Now, I'd like to hand over to Nathaniel to tell us more about Geomatic AI, how they're solving the challenges with vegetation management, and how they're leveraging machine learning to scale their vegetation management solution. Over to you, Nathaniel.
Thanks, Derek, and hello everyone. My name is Nathaniel Weldon, and I work at Geomatic.ai and specialise in developing geospatial AI solutions. Our suite of software and services called AIMS Optimize helps utilities to meet their regulatory obligations by automatically finding vegetation and engineering hazards so that crews can be assigned to repair the network, cut trees, and maintain line clearances. This reduces the risk of fire, reduces risks to safety, and reduces the length of unplanned outages. The service we provide, therefore, assists utilities to stay compliant with regulations at the same time as reducing their inspection costs. At the end of the day, everything we do at Geomatic.ai comes back to helping utilities serve each of their customers by maintaining a safe and reliable supply of electricity. To inspect a utility network efficiently, we start by performing surveys using LiDAR scanners. These laser sensors can be mounted on aircraft and ground vehicles and allow us to cover a large area very quickly. The scanner collects data that is assembled into a 3D point cloud, which we can then process using our proprietary classification and analysis software, producing a digital twin of the customer's network. So what exactly is LiDAR? LiDAR is a technique that measures distances using pulses of light from a laser. A LiDAR sensor can produce hundreds of thousands of such measurements every second, each one accurate to within millimeters. These measurements can be used to build up a 3D picture of objects in space. LiDAR scanners are used in a whole range of applications, including mapping over land and coastal waters, for navigation and self-driving cars, and even in climate research to measure water vapour and pollutant gas concentration in the atmosphere, and for space exploration, such as on Mars, for atmospheric research on NASA's Phoenix lander, and for navigation on its Ingenuity helicopter. The data that a LiDAR sensor produces is called a point cloud, which is an unorganised collection of three-dimensional points, each one representing a point on a surface in real-world space. We use LiDAR sensors to collect point clouds, but it's not the only way. At minimum, however, a point cloud stores the 3D position of each point, but it might also retain attributes such as the intensity of the reflected laser pulse, colour information, and the exact time the point was captured. There are several standard formats for storing point cloud data. These range from simple text through to advanced binary formats. Some of these formats are common in academia, but for our industry, the most important format is LAS, and its compressed counterpart, LAS-zip, or LAS for short. Our workflow from start to end is centred around the LAS format. Let's have a look at one of our completed point clouds. In this video, you can see a completed network section, or span, after it has passed through our classification and analysis processing stages. The classification stage decides what object each point represents, and the analysis stage then takes measurements between those objects to make a safety assessment for the line. You can see the trees marked blue and red, where the analysis engine has determined they are too close to the conductors and need to be cut. Our LiDAR classification engine is the first step in this process of Powerline safety assessment. Until recently, this was implemented as a rule-based classifier that made its decisions based on fitting the points to mathematical models of objects of interest. Alongside the point cloud, the legacy classification engine also required data from a geographical information system, or GIS, as an input. This GIS data stores the position of the poles and wires, and this was used as a hint to help classify the network assets. Once the classification stage is complete, the labelled LiDAR data is passed to the analysis stage, which uses the data to make various calculations that indicate the safety status of the power line, generally regarding the distance between the conductor and other objects. Once the analysis is complete, the system generates actionable reports, which can be managed using our FMC service or visualised through our AIMS 3D product. Here you can see some of the measurements that we take from a classified point cloud. The most important class to get right is the conductor class. In other words, labelling the wires that carry the electricity. Objects getting too close to or touching a conductor is what risks safety and reliability. Once we know where the conductors are, we can take measurements to nearby trees and buildings, to the ground, and even to other conductors to make sure that there is enough clearance around them according to regulatory requirements. GIS data is very important for managing a utility network, but as every data scientist knows, data inaccuracies are a fact of life. What particularly affects our process is when an asset is located incorrectly, which can lead to the classification engine missing or even inventing conductors and poles. We need the data to be correct to within about half a metre against the LiDAR, so before it can be used in our workflow, we send it out for manual correction. There are some automated tools to assist with this step, but a significant proportion of the work is still done manually. But relying on a manual process when we're aiming for very high processing volumes is quite limiting. The more the data deviates from real-world positions, the more work that we need to do to get it up to standard so that we can process with it. Because there's a significant manual component to this correction work, it's very labour intensive, relying on skilled human operators, which means that not only is it costly and really slows down the end-to-end process, it also severely limits our ability to scale up our processing. Let's assume that with all the corrections required, it takes an operator 5 minutes to apply all necessary fixes to a network span that needs manual review. If we have a total campaign of 40,000 spans and just 30% of them need a manual fix, then that's still 12,000 spans that need attention, totaling 1,000 person hours of labour. That's a big cost to the project and a big delay to delivery timelines. And when you consider that alongside our previous hand-coded classification engine, which is challenging and costly to develop, you can see why we needed to investigate a new approach to our LiDAR classification. Our goals for the new system were to improve the quality of our classification from our previous baseline while reducing time and costs. In particular, if we could reduce or eliminate our dependence on manually cleaned GIS data, then we would alleviate the major bottlenecks within the workflow that were increasing costs and causing delays. Machine learning seemed to be a natural fit for a new classification engine. When we're using ML instead of a rule-based system to recognize a new object type, we only have to retrain, not redevelop. In our case, it would also operate on the point cloud alone and wouldn't need GIS data. In fact, after ML inference has finished, we should be able to extract a cleaned GIS from the classified LiDAR. This would allow us to operate at much larger scales and lower costs. So we started on a journey to investigate whether machine learning would be suitable for our use case. What we're trying to do in our use case is to take a raw point cloud that totally lacks any sort of classification and assign labels to each point. We're particularly interested in 5 major classes: conductors, poles, vegetation, buildings, and the ground. So what ML techniques are available to do this task? While machine learning with point clouds is a relatively new field, researchers are actively investigating several subproblems. Similar to ML with 2D images, there are point cloud ML techniques for semantic segmentation and object detection. Semantic segmentation attempts to assign a label to each point in a scene, whereas object detection identifies discrete objects within a scene. They both have their particular application domains, but for our use case, it's semantic segmentation that is best suited to what we're trying to do. There are several semantic segmentation model architectures, and we investigated these during the course of our experiment. The point of switching to a new classifier was to improve the rule-based classifier that we already had. In any experiment, it's important to make sure that you're actually making an improvement. So to begin with, we established performance baselines based on the previous process, and from that, we calculated targets for cost savings and therefore return on investment. Let's go through how we built the LiDAR classification model that we're using. For any ML project, we first need to understand the data we're dealing with, and then select a suitable model that can meet the project needs. Every dataset has its own quirks, and every model has its own strengths and weaknesses, so it's important to think carefully about how to combine them to achieve the target business outcomes. The LiDAR data that we are using as training data is produced by our previous rules-based workflow, sometimes with manual corrections to the classification. As such, the classifications are quite fine-grained and constitute many more classes than we need for ML classification. For example, in the source data, we have separate classes for ground and road, but they are both types of ground, so we can condense them both into one class for training. Another example, we have up to 72 separate classes for conductors at each different voltage, but they are just variations of the same basic conductor. So for the purposes of classification, we can safely condense them into a single class. At the end, we train with just a few classes, typically 5, that represent all the rest. Another challenge is that LiDAR data is big. When uncompressed, a single LAS file can be anywhere from a few hundred kilobytes to several gigabytes in size. While data compression helps us with storing and transferring the data, there can still be many thousands of points in each file, even tens of millions or more. The volume of data depends on the area it covers, but also how it was captured. In general, the closer the sensor is to the ground, the denser the data. To help us manage the sheer volume of data, we not only compress it, but also built a database to catalogue every file available for training. This helps us to quickly target data of interest and extract a corresponding file set for training. Finally, LiDAR data is highly imbalanced. Let's have a look at this in detail. For our purposes of vegetation and asset management, we're particularly interested in the conductors. However, conductor points might make up around perhaps 0.5% of the total number of points in the scene, which is dominated by ground and vegetation. Because they represent the real physical world, this extreme imbalance is just a fact of life for LiDAR surveys. Point cloud semantic segmentation models commonly deal with this by weighting each class, which requires pre-counting a class histogram for the dataset before training begins and feeding this to a weighted loss function. As part of the experiment, the team, comprising members from both geomatic.ai and AWS, also investigated both downsampling and upsampling the dataset to further assist the training by adjusting the class ratios. The downsampling process reduces the volume of vegetation points in the training set while leaving the validation and test datasets as is. The algorithm works by first isolating clusters of vegetation using a dB scan algorithm. Starting with the largest, the clusters are progressively removed until only 20% of the original vegetation remains, at which point the dataset is ready for training. Using a clustering approach instead of uniform or random sampling is so that the natural shape of the vegetation is retained. The upsampling process, on the other hand, specifically targets the minority, conductor and pole classes to increase their proportion of the entire point cloud. The network assets are duplicated, repositioned, rotated at random, and then reintegrated into the rest of the point cloud and used as training data.
Before we explore the model building challenges and implementation, let's take a look at how geomatic AI defined its end-to-end experiment. The experiment consisted of a pre-processing pipeline and a model training pipeline. In the data pre-processing pipeline, geomatic AI experimented with 3 datasets. Firstly, an upsampled dataset containing more Powerlines and conductor classes. Secondly, a downsampled dataset with fewer vegetation. And finally, a dataset that combined both our upsampling and downsampling strategies. In the model training pipeline, geomatic AI explored training several semantic segmentation models, which I'll dive deeper in the subsequent slides. Now let's take a look at how geomatic AI built this data pre-processing pipeline in AWS. It begins with developing a custom pre-processing Docker image. By implementing a custom image, geomatic AI were able to utilize specific point cloud libraries to write their own custom data loader and implement the required sampling algorithms. This image is uploaded to Amazon ECR, a fully managed Docker container registry that makes it easy to store, share, and deploy container images. An Amazon SageMaker processing job is then used to create our resampled dataset. Amazon SageMaker processing is a fully managed data processing capability in Amazon SageMaker that allows you to run pre-processing, post-processing, and model evaluation workloads. In this case, Amazon SageMaker will read in the data from a source S3 bucket, process the point cloud files, and write it back to a target S3 bucket. Now that we've reviewed how geomatic AI implemented their data pipeline, I'd like to draw your attention towards the challenges geomatic AI encountered with training a point cloud semantic segmentation model and how they overcame these challenges. Starting with the data, the training dataset consisted of over 100,000 dense point cloud files, totaling 60 billion points, covering 2.5 billion meters across 3 networks. Training a model with such a large dataset meant that we had to find an algorithm that could both provide us with a good balance of efficiency, to keep the cost down, and accuracy to ensure that we met our target objective. To achieve this, we explored and established that we needed to experiment with several well-known point cloud semantic segmentation models. As we dove deeper into the models, what we found was that these models had frameworks with specific libraries and driver dependencies. As such, we had to develop custom Docker containers for each algorithm that we're going to experiment with. A word of advice: the container development can take quite a bit of time, and it was mainly due to semantic segmentation frameworks requiring specific versions for its library dependencies. Finally, many of these well-known point cloud semantic segmentation frameworks did not support less files out of the box, so we had to write a custom data loader to support this as well. To find the optimal model, geomatic AI not only experimented with different semantic segmentation models, but also with different underlying deep learning frameworks for each model. The reason for this was frameworks supporting the models behaved differently due to the differences in its implementation. And geomatic AI were looking to optimize the algorithm efficiency over its large dataset. As such, as each model implementation were different, they had different hardware requirements as well. Some models were more CPU intensive, and some were more GPU intensive. As such, to ensure that we could optimally train the model while leveraging the right hardware, we needed to test our training jobs with different hardware specifications. And this is where leveraging Amazon SageMaker training jobs helped Geometric AI not only train a model at scale, but also find the optimum price performance for the training job. Each point cloud semantic segmentation model was implemented using a custom Docker container deployed into Amazon ECR. Amazon SageMaker training jobs are then used to load the respective container images with a predefined hardware specification to train the models. By using Amazon SageMaker training jobs, data scientists at Geometric AI were able to provision the necessary hardware in minutes and train multiple models in parallel and at scale. Circling back to a 2 TB dataset, typically when training a machine learning model in Amazon SageMaker, data is loaded into the underlying EBS volume of the training instance when it started. However, as our dataset was significantly large, Geometric AI configured the training job to take advantage of fast file mode for Amazon SageMaker. Fast file mode combined the ease of use of the existing file mode and the performance of pipe mode. This provides convenient access to our data as this was downloaded locally, while offering the performance benefits of streaming data directly from Amazon S3. As a result, training can start without waiting for the entire dataset to be downloaded to the training instances. Now that we've seen what the data preprocessing pipeline and training pipeline look like, let's take a look at how Geometric AI put this together to automate a very iterative process in AWS. Starting with our preprocessing dataset, this architecture is probably familiar to you from previous slides, but with one key difference. Geometric AI implemented the processing pipeline using Amazon SageMaker pipelines to automate the deployment and triggering of the preprocessing pipeline. For training, once again, Amazon SageMaker pipeline was used to train the model, evaluate the results of the model by testing it against our test dataset, and if the results met the target accuracy, register the model in Amazon SageMaker model registry. This makes the model available for deployment into our inference pipeline, which we'll touch on shortly. Now that we've covered how we train a model, I'd like to touch on how Geometric AI brought this model into production by integrating it into its existing workflow. But before that, let's take a look at how Geometric AI integration requirements look like. The models Geometric AI trained covered different types of dataset. Some are more urban, some are more rural, and some are a mix of both. Furthermore, as highlighted earlier, Geometric AI experimented with several different algorithms. As such, they wanted the agility to run inference using one or more models at any given time. Secondly, the majority of Geometric AI existing vegetation management workflow processes relied heavily on AWS Batch. This had to be taken into consideration, and we had to weigh up the pros and cons of either using AWS Batch or leveraging something specific to machine learning, for example, Amazon SageMaker Batch Transform for batch inference. And finally, as a batch of incoming LAS files can vary in numbers and size, Geometric AI wanted to ensure that their batch inference process can scale accordingly. To meet the requirements laid out by Geometric AI, the classification workflow was implemented with AWS Batch. Using an AWS Lambda, the team was able to call different AWS Batch job definitions to run inference using a specific model. Upon execution, AWS Batch will pull the respective semantic segmentation inference image and train model weights from the model registry to run the classification process across the incoming raw point cloud data. Once the batch job is completed, the classified point cloud data is recorded in S3, and an event notification is sent to Amazon EventBridge and Amazon SNS to notify downstream systems for further analysis. Tying back together to the existing workflow, Geometric AI classification and analysis workflow starts with a LiDAR pre-processing job to split and catalog the incoming raw point cloud data from aerial and ground vehicle scans. The metadata is recorded in an Amazon RDS database, with the LAS file saved into Amazon S3. However, the GIS cleaning process is dropped from the pre-processing process and replaced with the machine learning classification process. Further downstream, an analysis batch job performs the conductor clearance analysis on the classified point cloud. This analysis job locates and identifies areas within the point cloud where vegetation is in close proximity to the power line. Segments on the point cloud where confidence level is low may be flagged for review, which involves the person manually reclassifying the points within the point cloud. Upon completion of this process, a report is saved into the state and storage layer. This report is then made available through a Geomatic AI's reporting system hosted on a server.
So, what results did we achieve with our ML project? You can see in this video the results of the machine learning classification model. You can see the unclassified point cloud on the left, and on the right, the same point cloud that's being classified using machine learning. This is a single large file of over 38 million points, and it was inferenced using a model that was trained with a completely different dataset captured from a different region. We're really happy with these results. You can see how buildings, trees, and most importantly, the network assets are all distinctly classified, ready for analysis and reporting. We're really pleased with the technical outcomes of the project. The new machine learning system met its accuracy targets, averaging about 81% across our 5 target categories. And really importantly, for our goals of safe and reliable supply of electricity, for the most important categories in vegetation management, which are conductors and vegetation, accuracy exceeded 90%. The infrastructure we've built for both training and inference using the AWS SageMaker and AWS Batch services is both flexible and scalable, and is well suited to meeting our LiDAR processing needs for both large and small customer projects. But if we turn and look at the business outcomes that are enabled by the technical outcomes, then the new system very much meets its goals. Using the machine learning workflow, we're looking at saving up to $500,000 per year through reduced reliance on manual data corrections. Reducing the human touch needed also allows us to scale up our operations and process more data in shorter time frames, improving throughput and reducing time to first report for our customers. This in turn helps them to manage any issues with vegetation and assets that we find on their networks and in meeting their regulatory requirements, while also keeping their workers safe by reducing the need for site visits. Meanwhile, automating the training and inference pipelines helps free our team from boilerplate and manual data management tasks so that we can accelerate our development and innovation. Let's return to the scenario that we put forward earlier, but this time with the ML classification engine. It might still take a human operator a total of 5 minutes to do all the necessary manual fixes, but if our improved classification means that we're only sending 10% of spans to review instead of 30%, then that's a major win for productivity. For a project of this size, we estimate that compared to the old rule-based system, the new machine learning classification will reduce manual labour from 42 continuous days to 14, for a productivity increase of 67%, which not only reduces costs and improves throughput, but also frees our workers to concentrate on the really challenging problems instead of routine issues. We're also really pleased with the classification workflow because it has enabled a new product offering for us. Because our AWS SageMaker pipeline is so flexible, we can offer classification as a service to third parties, where we can accept any LiDAR from any source, classify it and provide it back to the customer. So not only has moving to machine learning improved our previously existing processes, it's also allowed us to expand into new markets and explore new horizons for our business. Machine learning is an incredibly powerful tool, and we have a long list of plans for what we can do with it in future. We are looking to forecast vegetation growth, which will enable utility networks to proactively cut trees before they become a problem. We're also interested in helping utilities to efficiently assign jobs to work crews and assist them with in-field intelligence. And we're going to continue to push our models and systems further and further as we improve their classification performance and optimize the whole workflow for cost, while also investing in further expanding, refining and cataloging the data available to us for training.
To wrap up, I'd like to leave you with a few key takeaways from this journey we took with Geomatic AI. Firstly, before you jump into solving a problem using machine learning, it is imperative to understand what your business problem is. For example, are you trying to optimize the efficiency of a process? And once you've done that, you should quantify your problems in real-world terms. such as how much does the process cost, and what is the quantifiable efficiency gain? Once you clearly articulated your business problem and established that machine learning is a viable solution, you should start thinking about what key metrics will help you meet your business goal. In Geometric AI's case, we established a correlation between model accuracy and process efficiency, which led to them defining a target model accuracy as its success metric. Finally, when training a machine learning model for point cloud semantic segmentation, it is important to understand the nature of your data. You should ask yourself questions like, are you working with a dense point cloud? How large are my point cloud files? How many classes does my labeled dataset have? Are there instances where a single class dominates a point cloud? All these questions need to be answered to help you define your data processing methods, sampling strategy, and your choice of model. To help you with your machine learning journey in AWS, there are several options available from AWS experts, partners, and finally the option of doing it yourself. In Geometric AI's case, they work together with Amazon Machine Learning Solutions Lab to build a proof of value and to learn from the experts on how to build a machine learning model in AWS. And once they built a model that met their target accuracy, they work with AWS professional services to bring this model into production. If you'd like to further develop your cloud skills, we encourage you to get engaged with our training and certification content today. Scan one or more of the QR codes on the screen to get started with your cloud skills and training and certification. Thank you for joining us, and if you have any questions, do join us for our Q&A session immediately afterwards. We really value your feedback to help us improve our sessions, and would appreciate it if you could complete the session survey. I hope you enjoy the rest of ANZ Summit, and thank you for watching.